Minimization. Uh-oh. Yeah, that's right. All right. All right, get right. There you go. I guess that's clear.
Okay. So we're going to do optimization with two variables, Calc 3 style. But first, let's just go back to Calc 1 and do maybe one or two optimization problems, single variable. So these are always going to be, stories or word problems. If you guys remember from Calc 1, the setup is the hard part. The actual math and derivatives, it isn't that bad. It's simply just the setup, coming up with a picture, a story, and your two equations. That's the hard part of these problems. So it says a farmer has 200 feet of fencing. He wants to build a rectangular pen along a river. The goal is to create some sort of pin, find the dimensions that maximize the area of the pin. So I'm going to go ahead and just sketch a picture. So I've got some sort of fence or pin built along a river. I'm going to go ahead and introduce some variables. I'm going to call the length x and the width y. So for these optimization equations, you're going to have two equations. So first, we're going to start by finding an optimization equation. The optimization equation is the thing that you're trying to optimize, meaning the thing you're trying to find the maximum of or the minimum. We want to find the max area. So the equation that gives us the area that we're trying to find the max of, since it's a rectangle, that's just length times width or x times y. Now, if I wanted a maximum of this equation, then you can just say, oh, you make x as large as possible and y as large as possible. You have a maximum area. You can make them infinitely large. But in the context of the story, there's always something holding you back. A constraint equation. And the constraint is that you only have 200 feet of fencing. So again, the setup's always the same. Find an optimization equation. And if you want to minimize something, what prevents you from just making something as small as possible, making 0? There's always something holding you back. So identify a constraint equation. And the constraint equation here, well, if I need 200 feet of fencing, that means x plus y has to equal 200. Or x plus 2y equals 200. Questions? Yeah.
How do you know that you don't need 2x and 2y?
So if I'm calling this length x, since I'm built along the river, I don't need to put my fencing along the river. Okay, so step one, kind of read the problem, come up with a picture. picture, label some things. Step 2, identify your optimization equation and constraint. They're not always kind of blatantly given to you. You have to, use some context here. Like, I understood this means the perimeter, so I had to write an equation. Now, go ahead and solve your constraint equation for one of the variables. It doesn't matter what. For Calc 1, we're familiar with working with x's, so maybe go ahead and solve for y. Write this equation in terms of x. So now I have x times y. Got two different variables. We're in a Calc 1 setting. Don't know how to work with two variables. So we solve for one of the variables in our constraint equation, and then you can drop that into your optimization equation. So the area is x times y, and y is 100 minus 1/2 x. So now I'm just going to adopt that new kind of function notation and just say a of x equals, and now I have a function in terms of x. Our Calc 1 brain is happy here. I have a function in terms of only one variable. Just thinking about what this function gives you, you tell me x, which going back to our story, was just the length along the river, and this function is going to output the area of that pin. So if you want the maximum area, you can just take the derivative, find the critical point, find the maximum. So take the derivative, find the critical point, so set the derivative equal to 0. So we only found one critical point. So I have a sneaky suspicion as to what this is. But if we were being super precise, I would want to find the second derivative. And then I go through the logic, okay, if this is a critical point and the second derivative is negative, that means the function is concave down. At a critical point, you would have a maximum. So then the last thing we want to do is actually answer the question. What are the dimensions of the pin that maximize the area? Well, we're saying that x equals 100 feet. Now I need to find y. Don't forget, you have an equation for y. That's part of the process. You're always going to have an equation for the other variable. And y equals 100 minus 1/2 of x. So if x is 100, I get y is here. So now to find the max area, you could either, grab a times x, x times y, plug in x, plug in y. Don't forget, you also have an equation for the area in terms of x. So if you wanted, after you found x equals 100, you could plug 100 into this equation. And you know that's going to give you the max area given this x value. Either way you do it, doesn't matter. Throwing this at a calculator, I get 5,000 b squared. I just did x times y.
So you said the other way is to plug in x and then a of x equation?
Yes. Because this gives you the area based on x.
That's like in the case that you don't want to find y because it's like too complicated or something.
Yeah, could be too complicated, or maybe it didn't ask for it.
Oh.
Maybe it just said find the max area. That's the question. And after you found x, you can just plug it back in to find the actual. All right, that is an optimization question, start to finish, for Calc 1. Do we want to see another Calc 1 problem to get us warmed up, or we think we're ready to move to Calc 3?
Yeah, I don't know.
It's 100. Looks like Calc 1.
This says find the coordinates of x comma y. So find the coordinates of a point along f of x equals x squared such that the point is closest to the origin. So again, I'm just going to start by sketching a rough picture. Oh, I'm sorry, don't do it. Do x squared minus 1. So what this problem is saying is there exists some sort of point on this curve such that the distance to the origin is the smallest. So obviously grabbing a point all the way up here on my curve is going to be really far. Straight down is going to have a distance of just 1 since I was shifted down. The question is, does there exist some sort of point maybe in this general area that actually has the smallest distance? So again, the optimization idea is you're always maximizing something or minimizing something. So I need an optimization equation. And again, the setup is the hard part for these problems. So I want to make sure that you have a second to think about it. Try to write an optimization equation. Write a constraint equation. told me you have some general point x comma y on the curve. And if I want to be closest to the origin, it's saying that you want the minimum distance from the origin to x comma y. So I'm thinking distance function. So distance you could call d, but Calc 1 we're going to have to say like d something over dx. So just so I don't have like dd over dx, I'm going to call it L, just the length. So I'm finding the distance between this general point x comma y and 0, 0. And to make my life simpler, x minus 0 is just x, y minus 0 is y. So I get the square root of x squared plus y squared. That is my optimization equation. Now I need a constraint.
Is that constraint the given equation?
Yes, you're dancing around it. How so?
Because it's like, it says like the minimum amount of distance and
What is another way of saying f of x? Bam! There's your optimization, your constraint equation. It was right in a blind spot. So y equals x squared minus 1. That is your constraint, that the y coordinate needs to equal the x coordinate squared minus 1. One more time. That's the hard part of these questions, is just the setup. Now drop that constraint equation into your optimization equation. So I've got the square root of x squared plus y squared, where y is x squared minus 1.
That's your why. Right.
Reminding ourselves from Calc 1, the derivative of square root of something is 1 over 2 root x. If you think of that as x to the 1/2, sure, you can drop the 1/2 down and subtract. If you simplify, we just locked in our brains, derivative of square root of x is 1 over 2 root x. So doing some chain rule, I can do 1 over 2 times the square root of the inside times the derivative of the inside.
Okay, I see that. Okay. That's what it is.
So just stare at that for a second, make sure we're convinced. The derivative of square root of something, 1 over 2 root something, times the derivative of the inside. 2x plus, this is now a chain rule. Drag the power down, subtract 1 from the power, keep the inside the same, times derivative of the inside. If you're wondering, hey, could I have just FOILed that out? Sure, you do the same thing. So I'm just going to write this in the numerator, maybe distribute that through. I'll do it in 2 lines. 2x plus 4x, x squared minus 1. questions on just the derivative? All I did here was write this in the numerator, just say 2 times 2x is 4x. And then in this next line, just distribute 3. So to find critical points, I want to know where does our derivative equal 0. Two schools of thought here. You could either say, okay, I know a fraction equals 0 whenever the numerator equals 0. So you could just set the numerator equal to 0. You could think of it as, well, what if I multiply the entire bottom to the other side? Then anything times 0 is 0. So you're still left with the numerator equals 0.
Only left with it.
Oh, I can combine my terms. Could have done it a lot better. 4x to the third minus 2x equals 0.
So instead of doing the quotient rule, you.
So are we thinking quotient rule here? Don't forget, this is the derivative. I just need to find where the derivative
Is 0. Okay. All right. Okay. Yeah.
So now, we might say, oh, well, second derivative test. I don't want to take second derivative. So one of the tools that we utilized in Calc 1 was doing this line test, where we're marking a sign chart for values of the derivative. If we wanted to clean this up, square root of a fraction, you can take the square root of the top, square root of the bottom. And if we were super particular, and we wanted to rationalize, you could multiply by root 2 over root 2. So this is just a sign chart. And I'm just going to grab values in between. So if I grab something to the right of root 2 over 2, maybe like 100, I'm just going to exaggerate. And I want to plug that into my derivative and see what I get. Just for the sake of time, I will let you know that you get plus, minus, plus, plus. Again, what am I doing? I'm just grabbing values in between, grabbing a calculator and plugging it into the grid. I get a positive number, don't care what the number is, I'm going to mark positive. We can see a maximum where the derivative changes from positive to negative. I can see a minimum where the derivative changes from negative to positive. So now let's go ahead and just bring it back home. We have 3 points. This general point x comma y, I know the minimum distance is root 2 over 2 comma something. I haven't found the y coordinate just yet. I have the coordinate 0 comma something. And I also have the point negative root 2 over 2 comma something. And just kind of thinking about it picture-wise, my distance is shrinking till I get to this minimum distance and then starts to go up again. And just due to symmetry, the same thing happens over here. You get the mirror image. Distance starts to decrease and then increase, so minimum. And based on that sign chart, x equals 0 is a maximum. Distance starts to increase, distance starts to decrease. To find the y coordinate, I can now plug it into this equation.
Square. Just 2. Yeah. Oh, shoot. Sorry. 1 half. 2 over 2. 1 half. Negative 1 half. 2. Damn it.
So now coming over here, I know these have y coordinates of negative 1 half. That is a y coordinate of negative 1.
Nice.
The Calc 3 problem we're going to do is pretty similar, so please ask questions.
So can you repeat that thing about the, like, when it goes negative
Yep.
to positive?
So if the derivative changes from negative to positive, the derivative is negative, the function's decreasing, derivative is positive, the function's increasing, that means the original function changes from decreasing to increasing. So that is carving out a minimum. You see a sign change from positive to negative, function goes from increasing to decreasing, that's carving out a maximum.
So negative to positive is minimum, positive to negative is maximum.
Yes.
And that increasing decreasing just basically means it passes the x-axis when you're looking at the dx graph. Or the
Say that one more time.
Like, positive or negative just basically means it passes the
Yes.
x-axis. On that graph, right?
On the graph of the derivative.
Okay.
Okay, so I took 2 seconds and kind of just drew this in Desmos just so we get a visual understanding. So this dashed red line here represents the distance from the origin to this point along the curve. So just kind of dragging this, just cosmetically, you can see that the length of that line segment going on decreases. This is definitely some sort of minimum here. Then it starts to increase till we get a maximum, and then starts to decrease till we get a minimum extending to forever. So if you look at this box over here, this is now displaying the distance. And numerically, you can see that we are decreasing, decreasing, and then it starts to look like increasing again. Increasing, 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 starting to decrease now. And if we type in exactly square root of 2 over 2, this is the minimum distance. We are now going to extend this to Calc 3, but first I'll show you one more.
And question with that, even though it's concave up at the, I guess it's not a minimum value, it's a maximum down there. Even though it's concave up, it's a minimum here. Instead of concave down where it should be a maximum, but it's actually a maximum here.
Oh, hang on one more time. I want to make sure I understand. Yep, so you're saying the original function is concave up?
And I'm getting a max instead of a min. Because normally concave down, you'll have a maximum.
So maximum, the second derivative is 2, so concave up. I got it. We're thinking of the graph of x squared minus 1, which I agree is concave up. But we actually want to be considering the graph of our L equation, which was the square root of that thing.
Okay.
You want to consider the concavity of that function. So just giving you kind of another Calc 1 example, we're going to look at the Calc 3 variant of this one. You can draw some sort of rectangle underneath a parabola. The question in Calc 1 was, find the dimensions of the rectangle that maximize the area. So you can see of all the different rectangles that are possible, there exists some sort of rectangle that you can draw where you get a max area. We're going to do that same idea for Calc 3. All right. You're ready to look at the Calc 3 equivalent. But now that we did 2 really good examples of Calc 1, I promise this is going to seem pretty straightforward. Already reading it feels pretty similar. Find the point along the plane that is closest to the origin. So in Calc 1, we have a curve. So I'm drawing a line segment. We're finding the minimum distance. Now I have some sort of plane in space. And I want to find the minimum distance to that plane. Let me give you guys a second to just try that out on your own. I'm going to work on getting Desmos to draw a picture of this. go ahead and look up at the projector. I have Desmos graphing what this problem is talking about, just visually so we understand what we're doing. I have some sort of plane in space. And the goal is to find the minimum distance from the point to the plane. So I have some arbitrary point along the plane. And I want to find the distance such that this line segment being drawn to the plane is at a minimum. So you can kind of get an eyeball of maybe around where I would have to go. But algebraically, we want to find that. Yeah.
So for the question, would this like for sure be a criteria question, or will we have some multiple choice?
So definitely RQ. Maybe I would ask you to simply write the equation with the constraint plugged in. We're going to go CS. Bruce. Yep. And then you want to find where each partial place is.
And this would be on the test as well, right? Correct.
So yes, but kind of like the last section, maybe we're thrown in, maybe just give me the setup, but don't actually find it. Maybe here's the setup, maximize it. But some of these problems that you guys are realizing, yes, it's hard to ask a question like this so I can finish. So again, it feels pretty similar. I've got 2 points, 0, 0, 0, the origin, and now x, comma, y, comma, z. So my optimization equation is my distance. That is the square root of x squared plus y squared plus z squared. How do I find the constraint?
We just use our equation and switch it around where we solve for z.
Yep. So now just find something to plug in for z in terms of x and y. And now thinking back to Calc 3, I've got a surface with only 2 variables. You have this equation up here. Go ahead and just solve for z. Now you can drop that z equation into your optimization equation.
Okay, and why are we using z instead of x or y?
Great question. It turns out you can't. You could have solved for x, and then you had something in terms of y and z. Personally, I'm used to, just like for the Calc 1 example, how we solved for y to put it in terms of x, you could have done it in terms of y.
Okay, but because really,
I'm used to doing it in terms of x.
because your f of x and y gives you a z value.
Yes, but what I'm saying is you could have f of y comma z that
Mhm.
gives you an x value. It's just more
Okay.
traditional to think about it as
Okay.
plugging in something for z.
Physique, got you.
All right, this is where we want derivatives. Don't forget, we're back in Cal 3. So we need partial derivatives.
Partial. Fun,
So you're going
fun,
to
fun.
find two derivatives. The partial derivative with respect to x, the partial derivative with respect to y. Your critical point is where both of those equations equal 0. So partial derivative with respect to x only. The derivative of square root of something is 1 over 2 root something times the derivative of the inside. But we're doing partial derivatives, so anything that's a y is treated as a constant. Derivative of x squared is 2x. Derivative of y squared drops out. This is now a chain rule. Drag the power down, subtract 1 from the power, keep the inside the same, times derivative of the inside, constant, derivative of negative 2x is negative 2, derivative of y is a constant. Please stare at that for a second, make sure we're convinced. Yeah.
Could we have like distributed the square?
This one?
Yeah.
Yeesh. But I've got a trinomial? That's pretty ugly.
16 y squared.
Yeah, you'd have to, it would be a lot.
La la.
If it's a binomial, you just FOIL it, it's not too bad. Two trinomials, I might just make sure I know some change.
And then you figure you taking your 2 down, 2 minus 1 is 1, then you just taking the derivative of the inside. Not less work.
So again, I'm just going to clean it up, write it to where it's in the numerator.
The power down, power down, power down, power minus 1.
Now I'm just going to distribute. I want to give you guys a little bit of a head start for the partial derivative with respect to y. Same idea, but now in your chain rule aspect, we're just taking derivatives with respect to y. derivative of square root of something, I've got 1 over 2 square root of something. Times alright, derivative of the inside, derivative of x squared, now with respect to y, is just 0. Derivative of y squared is 2y.
Bring it to that.
Drag the power down, keep the inside the same,
It's just times 1.
subtract 1 from the power, times what is the derivative of the inside?
1.
So I'm actually a lot better off on this one.
Mhm.
Just going to clean it up.
Crazy question. Why are you putting 1 over the square root?
So it's just kind of locked in our toolbox.
Mm-hmm.
The derivative of the square root of something.
Right, it's 1/2 over the square root of x. Right. Okay.
So in general,
You just
derivative of square root of something is the
Just
derivative
one
of the something over 2 times the square root of something.
okay. So you just right away just go ahead and
So I think in Calc 1, when we're first seeing it, we rewrite it to the 1/2 power.
yeah.
We've done so many that we can lock in that I understand that this will simplify. The derivative of this will simplify. Okay. Please ask questions on just so far. Identify an optimization equation and a constraint. Plug the constraint into the optimization equation, and now you get a function in terms of x and y. So you can find the partials with respect to x, partials with respect to y. And now I can go ahead and set them both equal to 0. Now, just like last time, if we have a fraction equals 0, we said, oh, it's when the numerator equals 0. So just coming up over here, I'm just going to write that the numerator, 10x minus 16 minus 4y equals 0. Looks like I can divide everything by 2.
5, 8, 2.
And so far unhelpful. I didn't land on like, oh, x equals 3, x equals 4, y equals 7, nothing like that. So let's grab our partial with respect to y. Set that equal to 0.
5 by 4. That one. 1, 1, 2.
Again, I didn't get any clean numbers.
But you can solve for, you can solve for
You can
x
solve
or y.
using either substitution or elimination, up to you. To me personally, this is screaming substitution. If you ever have a coefficient of 1 for one of the variables, I'm just going to take 2 seconds, solve for y.
Right.
And then just drop that in the other equation.
2x minus 4. 2x, 8x, 12. 8x, 12. No, minus 2/3. -2/3.
Okay. Questions on just the algebra of the solver?
It's a lot. But if you step by step, and if you do make a problem, as long as you step by step, you can go back and find it. Make a
So
mistake,
I have
I
a
should say.
critical point. What we should be doing now is, to be super precise, we should actually verify that this is a maximum. You would use your second derivative test. You would need your mixed partials. I'm going to absolve us of that. I think we only have the point. Sketching this, we can see that this is going to be a minimum. But to be super precise, we should verify using our second derivative test that we did a minimum. Let's go back all the way to the beginning now and actually verify that. Let's actually answer the question. It said find the point on the plane. Well, that's a 2D point, so that is not living on the plane. What's the very last thing that I need to do?
Plug in the X and Y constraint.
Yep. Find the Z coordinate. And as always, you're going to have an equation as Z equals something, because that was the constraint that we plugged in. So 4 minus 2 times X, which is 4/3, plus Y, which is 2/3.
Four-thirds minus 2/3
Thank you.
is 2/3. Two-thirds is
Okay. Last thing I'm going to leave you with that you guys are actually gonna really like. Let's bring up that visual again. And I'm going to write our answer just over here so we can see it. The point was 4/3, negative 2/3, 2/3. When we were looking at that visual, kind of just moving those sliders around, trying to find the minimum distance. I didn't want to show this visual long enough because I feel like someone could have maybe figured it out. Where does this line need to be kind of quote unquote pointing in such a way that you get a minimum distance? Well,
distance.
at a perpendicular.
Yeah,
Orthogonal, what relationship would that have with the plane?
The plane.
Some
It would-
some vocab words.
It would be the normal vector to the
It
plane.
would be the normal vector to the plane. So it's almost like whatever the normal vector to the plane is where that point should be.
Wow.
So do,
Let's go all the way back to the beginning now.
Yeah, right.
What is the normal vector to this plane? You can actually do it by perfection.
2, -1, 1.
Let's grab our point here and now treat the point
You're gonna write the line.
as a vector. You could divide everything by 4/3. I'm going to do it in just 2 lines. Multiply everything by 3.
Right, 3, right, 4, -2, 2. Okay.
Divide everything by 2.
1, 1. Look at it, bang. Ha.
but what
That's
is
the normal
point
vector.
that?
Say again?
Why is it point that?
This is like the location. This is kind of where that is pointing.
Wait, okay,
So it can be a scale.
One's a vector, one's a point. Yeah.
We didn't have to do any of that, we just had to look at that.
This just has this one problem has a nice.
One problem?
Yeah.
Okay, take that.
Why is it just this one
Yeah.
problem?
Yeah, basically.
Because we know about planes and we know about perpendiculars. I could have said, the point perpendicular to any other point, it's still going to be, perpendicular but passing through a different point. It's just kind of cool because in Unit 1 we spend time with planes.
Yeah, and now putting it all together, it's like, okay, the math works.
So now flipping the page, I just want to give you a visual on number 2 before I leave. A rectangular box is resting on the XY plane with one vertex at the origin. The opposite vertex lies in the plane. So this is kind of the analogy to Calc 1 where we have the rectangle under the parabola. Now we're going to have a prism, or rectangular box, underneath some sort of plane. So before I pull up the visualization, just take a second. Visualize in your head, you have a prism or a box sitting on the XY plane with one of the vertices or corners at the origin.
What's the volume in a 3D space?
Length times width times height. So here's your visuals of that. I've got the plane that was given to us, and I've got some sort of box where one vertex of this box or prism is at the origin, and the opposite one is touching the plane. So there are lots of different prisms that you can draw. X and Y can be anything here. I've got 2 different things that I can be moving around. So this box can be, super tall and skinny in the Y direction. It could be, long ways, skinny in the X direction. And then the height is controlled based on what X and Y
Z,
is.
right. It makes sense.
Because I have to live underneath the plane. You can see in that very top box, that gray box is computing the volume of all the different prisms. Well, if we want to find the max volume, we're going to find the dimensions of this prism, x by y by z, that give you the max volume.
Right.
And then find the volume.
And since you can't have a negative volume, it's only positive Z values?
Yes, yeah. Now, when we end up doing our equations and doing our partials, the problem itself won't have any understanding of that, and we'll probably try to compute everything. But we understand we can constrain this to be just positive Z. So there's your visual there. We need an optimization equation and a constraint. Before I send you off, I do want to send you off with just those 2 equations, so we at least have a head start. So the way to quote unquote get the point is to have the sliders on until you see a max volume. But since I can change both X and Y, I think it'd be okay. Now you can eyeball it where it's going to be. I have a feeling that, you know, the most cubish box, the better. It turns out super tall and skinny, even if it's, you know, 10,000, is not going to give me a lot of volume. Again, kind of a cube like would give me the most.
6. So max. It's around 6 of them. So it's around. I think it's like when it's the.
So what is my
non-vector.
optimization equation here if I want to maximize the volume?
For your Z.
Say again?
Your Z is.
Yep, so I'm going to say x times y times z. You could call it other variables, but just because we're living on the xyz space. My constraint equation, again, is just take 2 seconds, solve for z.
Yeah. 2x 4/3 y minus 24 equals z. Ooh, I'm wrong with that.
We just wrote it in a different order.
Okay. Oh, and then you. Okay, yeah. I didn't. Okay, right. 3 divided into 24 is. What's the again? Can't multiply. 8. Yeah, 8. Okay. Right. Wow.
So looking at this one, I will let you know this one's actually going to be pretty straightforward. Because if you can distribute this through, you've just got some simple power rules going on. There's no ugly square roots. There's not even change. You guys are going to like this one. All right, so I have the rest of this project for you guys to have a chance to work on over the break. We won't be on Friday. So we'll go ahead and do this.
Oh, okay, yay!
But then after the break, we have, you said one more class, like a study review, and then.
No, we'll hang out a little.
What would
probably-
you recommend, like, the best thing to do over break calc-wise? Like, what should I be studying?
That's a good
lot?
question. I will try to make and post practice tests.
Yes.
I am going on a cruise, so give me some time.
Nice.
Sorry.
Congratulations.
But I will try to post some practice tests of maybe just things we've done so far.
Thank you very much.
Kind of like what we had with exam 1, where we had like a few different practice tests.
Say again?
Kind of like with exam 1, we had a few practice tests.
And then we'll probably spend, if I had to guess, a class doing optimization again. We've got one more lesson, and then review and test. So with that, it sounds like we'd be on track for the Monday after we get back. Okay.
All right.
And try to enjoy the cruise.
I'll try.
Yeah. I can sit down with your laptop doing work. Yeah, no, try to enjoy it. Man.